Hi, welcome back. In the previous module, we spent a lot of time thinking about demand and supply and how they interact in the market equilibrium. The market equilibrium is a very powerful tool in economics. But at times, you might feel that the tool is quite arbitrary. Because if I put in one demand function as opposed to another, the market equilibrium is going to be different. And the properties of the equilibrium is going to be different. So how much faith can I put into these tools or the results that are generated from the equilibrium? Therefore, it is very important for us to understand where do demand functions and supply functions come from, and what kind of underlying assumptions are driving the properties of different demand functions. In fact, we're going to dedicate a large proportion of time in this class to address these questions. The next major module is going to address what we call the consumer's problem, or otherwise known as utility theory, that gives rise to the demand function. From there, we can gain a much deeper understanding of where demand functions come from, what kind of assumptions or structures are behind such demand functions, so that we would understand in what scenarios a particular demand function may be appropriate or not. So what do we mean by consumer's problem? Well, the idea is simply that for any consumer to make a consumption decision, the consumers are constantly trying to make careful choices according to their own preferences of different products, given the limitation of the resources they have on hand. And once we have a way to model the preferences of consumers, and also have a way to model the resources they have, then we can put these two components together, and then we would have a model of consumer's choice. And that's the objective of this section. We'll spend a lot of time thinking about how to model consumers' preferences, how to model the resources they have, and once we put these two components together, hopefully the model can give us a better understanding of how consumers would make certain choices when they're given a particular environment. So first, let's dive into preferences. We understand that every consumer, every individual in the world would have different preferences. Some people may prefer steak over salmon, some people may prefer sneakers over Crocs, some people like Macs over PC, others prefer PC over Mac. You can say the same thing about iPhone versus Android phone, skateboard versus bicycle. And even when it comes to relationships, some people may prefer a more romantic relationship, while others might prefer a more practical relationship. Everyone has different preferences. And these different preferences are key drivers of how we make consumption choices. So in order to have some meaningful model of consumer choices, we need to first be able to model preferences. That's obviously a very daunting task. So a very useful baseline to start with is just to focus on preference relationships that are particularly logical. And that's what we'll focus on within the scope of this course. You might ask, what if some choices are no longer very logical or rational? Well, then we move into the scope of behavioral economics. We won't have much time in this course to discuss the details of it, but our department does offer a behavioral economics class from time to time, and that course will address these issues more specifically. So now let's dive into the notion of preferences, at least what we mean within this course. The next few slides will be one of the most abstract lessons within this entire course. So bear with me. I promise that the end is going to boil down to something very concrete and specific that we can work with. But the process of getting there may seem quite abstract. So don't freak out and just bear with me. Our approach here is to introduce several definitions in turn. And all these definitions combined will make it very specific about what we mean by logical preference. So we'll first define a preference relation, and we'll use this squiggly kind of greater or equal to sign, and we'll call it weakly preferred to. Note that this notation does not look exactly the same as a greater or equal to sign because of its wavy edges. So it's really describing a preference relationship as opposed to comparing two different numbers. But you will realize that just like the similarity in the symbols, these two ideas share a lot of commonalities. Let me give you an example that help us describe what we mean by this preference relationship, weakly preferred to. Let's say we have two packages of goods. The first package is called A, the second package is called B. And they have different contents within them. So if a consumer prefers package A over package B, we're going to write A is weakly preferred to B. That's it. It's as simple as that. It's simply a comparison between two packages of possibly different contents. And the sign itself simply conveys the idea that the consumer prefers one over the other. For example, if I walk into a sandwich shop, I might be presented two different choices on the menu. So different consumers may like one or the other. But if my preference is such that I prefer the combo that has one sandwich and one apple over the other choice that only has two sandwiches but no apple, then we'll simply write that this bundle here with one sandwich and one apple is weakly preferred to this other combo that has more sandwiches but no fruit. So in fact, this weird looking notation is simply helping us to describe these very intuitive ideas. Just like we can have strictly greater to when we have greater or equal to, we can have strictly preferred to when we have weakly preferred to. For example, if I strictly prefer a bundle that has one bagel and one cream cheese over the other combo that has two bagels and no cream cheese, then I would write one bundle is strictly preferred to than the other. What it means is that these two bundles are never the same to me. I would always choose one over the other. Whereas looking back to weakly preferred to, it is possible that I feel the bundle with both sandwich and apple is better than two sandwiches and no apple, or they are about the same. In the second scenario, when I use strictly preferred to, they're never the same. I always prefer one over the other. And once we have these two notions in place, we can also define something called indifference. And the way we write it is simply this wavy sign here. And we'll read it as indifferent. For example, I may feel that a breakfast bundle with one cup of coffee and one croissant is exactly the same to me as a bundle that has one cup of tea and one cake. One is not better than the other. And with these notations in place, we'll be able to describe in a relatively concise manner about what we mean to say that a preference relationship is logical. The preference relationships we discuss within the scope of this course is well defined by three different properties. They're called completeness, transitivity, and non-satiation. Well, what do we mean by that? It means that for all the preference relationships we consider and trying to model in this class, they must all satisfy these three fundamental properties. Now let's go through each one of these in turn. First of all, we say a preference relationship is complete if any two bundles of goods can be compared. Specifically, if you have any two bundles of goods, A and B, then they must fall into one of those three possible outcomes. We'll either have A is preferred to B, or B is preferred to A, or both, in which case it just means they're indifferent. Well, this is a very natural property. What it says is that the consumer is able to make comparisons for the possible combinations of products that we're concerned with in a particular context. The second property is called transitivity. We say a preference relationship is transitive if for any three different bundles of goods, A, B, and C, if A is preferred to B and B is preferred to C, then it must be true that A is preferred to C. And this is really the part of the property that gives us a very logical structure to the preferences. For example, as a consumer at a coffee shop, if you know that my preferences are such that I prefer 1 cup of coffee and 1 croissant over no coffee and 2 croissants, while at the same time you know that I prefer no coffee and 2 croissants over 2 coffees and no croissant, then you hopefully will be able to reliably deduce that if I'm a logical person, I would also prefer 1 cup of coffee and 1 croissant over 2 cups of coffee with no croissant. Well, otherwise, you would run into a loop of preferences where I prefer A to B, B to C, but then C to A. In that case, it will be really difficult for you to figure out what is the bundle of goods that I would end up purchasing according to my preferences. So we would require that the preference relationships we consider are ones that satisfy transitivity. Within the realm of preference relationships, we would say a preference relationship is rational if it satisfies both completeness and transitivity. Because then you can present different bundles to this consumer, and this consumer will be able to tell you how they compare against each other, while at the same time, with a sequence of comparisons, all the results are logically consistent. In addition to these properties, the third property we require the preference relationship to hold is usually called non-satiation, or sometimes called monotonicity. What it means is, given that I have the same amount of one good, I would always prefer more of the other good. For instance, if you give me 2 cups of coffee, I would always want more croissants. Well, you might say that's unrealistic. I would never want to have 15 croissants for one breakfast. However, this kind of restrictions are context specific. In general, if you think of me as a long-term consumer of breakfast, I would usually want to have more goods. This property, although a little bit unrealistic in some context, gives rise to a lot of convenience in our analysis and modeling choices. And we can discuss later on how relaxing this restriction changes the model. As we discussed previously, because everyone tends to have different preferences over things, it is really difficult to think about a general way to describe such preferences that can encompass many, many different ways of thinking. Although most people would disagree on their most preferred choice of breakfast combination, but we do believe for most consumers, it seems reasonable to think of people's preferences as being complete and transitive. And as it turns out, that as long as you're willing to accept these two restrictions on preference relationships, we're able to represent people's very abstract preference relationships using something very intuitive and visual. And this tool is what we call the preference map or indifference map. It turns out that these very intuitive visual graphs are able to represent the very complicated preference relationships we have. So now let's take a look at a particular example of this. When it comes to lunch choices, people may prefer different combinations of pizzas and burritos. And as different combinations of possible lunch choices, we might imagine someone consume a lot of pizza and not that many burritos, or a lot of burritos and not that many pizzas, or a lot of pizza and a lot of burritos, or not much of either one. So when presented with different combinations of pizzas and burritos, we expect consumers to have a preference over them. Although I might be more of a pizza person, and you might be more of a burrito person, but it turns out that as long as our preferences satisfy completeness and transitivity, we're able to use a graph to represent these preferences in a very straightforward way. So what do we mean by that? First of all, in any one of these maps, we will be able to represent any combination of the two choices with a coordinate or a dot on this map. Let's look at figure A for now. For instance, this particular point E is representing a bundle that has 25 units of pizza and 15 units of burritos per semester. Now if we look at point F here, point F will represent a different combination, which has 30 pizzas per semester and 20 burritos per semester. So comparing F to E, we're having more pizzas and more burritos. But if we look at point D here, point D will represent a bundle that has less pizzas and less burritos comparing to point E. So by the restriction of non-satiation, the consumer always prefers more goods. What do we mean by that is that the consumer would prefer bundle F over bundle E over bundle D. And the reason is because bundle F offers more of both goods than bundle E. Therefore, F is better than E. And bundle E offers more goods than D. And therefore, consumer will prefer E over D. So although I may be more of a pizza person who values consumption of pizza more than burritos, whereas you might be more of a burrito person, but we would both prefer E over D and F over E, as long as our preferences both satisfies non-satiation. This illustration shows us that non-satiation alone gets us quite a bit of traction in comparing different bundles that are available to consumers. However, if you look closely at the graph, although we're able to say by non-satiation that any combination in area A is preferred to any combination in area B, it's very difficult for us to make a comparison between combinations such as C versus E versus A or B here. And the reason is that if you compare C to E, non-satiation doesn't really give us a clear answer of which combination is better. Because E offers more pizza than burritos comparing to C. So as a more of a pizza fan, I may prefer bundle E over bundle C, whereas as more of a burrito fan, you might prefer bundle C over bundle E. So how can we use this tool to help us compare these types of bundles? Well, this is where the notion of indifference curves start to be really powerful. Now let's shift our focus to figure B here on the right-hand side. This little curve here called I superscript 1 is what we call an indifference curve. What we mean by this curve is the following. Notice how this curve passes through many different bundles in this pizza versus burrito space. What this line indicates is that this consumer is indifferent between all bundles along this indifference curve. In other words, this particular consumer would be indifferent between bundle A versus bundle E versus bundle C. As we move from bundle A to E to C, this consumer is giving up pizzas in exchange for burritos. But now, with the help of the indifference curve, we're able to figure out what kind of replacements are exactly indifferent in the mind of this particular consumer. What's more, the power of the indifference curve combined with non-satiation is that we're now able to compare any bundle in this graph. Let's see how that works. As we were previously talking about, in figure A, it is very difficult to make comparisons between points such as C versus points such as B. If we look at point C here and point B in figure B, it turns out now, once we have an indifference curve in place, we will be able to make a comparison. And my argument is going to be that this particular consumer prefers bundle C over bundle B. Can you think of why? Well, it is really a combination of the definition of indifference curve and non-satiation. Although we cannot compare C versus B directly, but we're able to compare A versus C. And with the help of the indifference curve, we now know that bundle C and bundle A are indifferent for this particular consumer. On the other hand, non-satiation is telling us that this consumer must prefer bundle A over bundle B, because A offers both more pizza and more burritos than B. Now once we have transitivity in place, we already know that this consumer is indifferent between C or A. In other words, the consumer weakly prefers C over A and A over B. Therefore, this consumer must also prefer C over B. And similarly, we can deduce that the consumer would also prefer bundle E over bundle B. Again, not an easy conclusion we can draw by just looking at figure A alone without the help of the indifference curve. It turns out that indifference curves is a very powerful tool that can help us represent a general set of very complicated preference relationships, which offers a way for us to start model preferences and start draw implications from it. It is therefore very important for us to discuss the essential properties of indifference curves. It turns out that indifference curves has to follow a particular set of rules, and these properties are all rooted in the three fundamental requirements we imposed on the preference relationships: completeness, transitivity, and non-satiation. Now let's look at what these three properties imply in terms of the representation we have in the preference map. We have already seen a little bit of the first property on the previous slide, and to generalize those insights, essentially what happens is that the indifference curves allow us to make comparisons over any consumption bundles that are available in a two-product space. Specifically, any consumption bundle towards the upper right corner of the indifference map is preferred to comparing to combinations that are very close to the origin. Moreover, the indifference curve itself helps us carve the entire product space into three areas. The first area is just along the indifference curve itself. All the consumption bundles lying on the indifference curve are indifferent by definition. But more importantly, any bundles along an indifference curve is preferred to comparing to all the bundles that lie below the indifference curve towards the lower left corner. Similarly, any bundle towards the upper right corner of the indifference curve is more preferable comparing to any bundle lying on this particular indifference curve that sits below those bundles towards the lower left. Now consider an even richer map. In addition to one indifference curve, in fact, we can have many indifference curves. And the reason is because once we choose any bundle, the consumer can also start to list many different bundles that they felt are indifferent to the particular bundle that already presented to them. For instance, here, bundle C would be indifferent to bundle E, and we know that bundle F is more preferable comparing to bundle E and C, but also there are many other bundles that are just indifferent comparing to bundle F. And similarly, we know that bundle C and E are more preferable comparing to bundle D. But also we know there are many other combinations of goods that are just as preferable. Of course, they're all less preferable comparing to E and C. In fact, when we have multiple indifference curves, any bundle that sits on a higher indifference curve towards the upper right is always more preferable comparing to bundles that are sitting on the lower indifference curve towards the bottom left. In other words, the indifference curves are ordered. All bundles on I3 are more preferable comparing to bundles sitting on I2, which in turn are more preferable comparing to bundles sitting on an even lower indifference curve of I1. The second property of the indifference map is that every bundle sits on one and only one indifference curve. In other words, you will never find a bundle that does not belong to any indifference curve. Meanwhile, any bundle will only sit on one and one only indifference curve. The fact that any consumption bundle must belong to an indifference curve is because of the property of completeness. Because the consumer is able to make comparisons between any two combinations of goods, it must be the case that a particular consumption bundle is preferred to or less preferred to a different consumption bundle. As a result, it must sit somewhere along some indifference curve. The second part of the statement that says any consumption bundle can belong to only one indifference curve overlaps with our third property that says two indifference curves cannot cross. Well, why is that? Suppose we look at the case in figure A here, where we have two indifference curves crossing at point E. Then consumption bundle E would be sitting on two different indifference curves. And of course, these two indifference curves would be crossing. However, this cannot be the case because it is contrary to the three simple properties of preference relationship we put in place. Let's see how that works. Because of the fact that these two curves, I0 and I1, are both indifference curves, then by definition, all the consumption bundles along each of them are indifferent. The implication is that by the definition of I1, consumption bundle B and E are indifferent. And by the definition of indifference curve I0, consumption bundle A and bundle E are indifferent. And therefore, by transitivity, we must have that consumption A and B are indifferent. But now it becomes a contradiction to non-satiation, because clearly consumption bundle B offers more of both goods, and therefore, because the consumer's preference must satisfy non-satiation, the consumer must prefer B over A, and therefore they cannot be indifferent. In other words, if we have two indifference curves cross each other, the represented preference relationship cannot satisfy the three properties we stated previously. In other words, as long as we focus on preference relationships that satisfy those three properties, we would never have indifference curves that cross with each other, or having any consumption bundle that sits simultaneously on two different indifference curves. Property 4 says that any indifference curves must slope downward. What if that's not the case? Let's look at figure B here, where we have an upward sloping indifference curve. By the definition of an indifference curve, any two bundles lying on this curve must be indifferent, and therefore bundle A and B must be indifferent to each other. However, this is clearly in contradiction with, well, you guessed it, non-satiation, because bundle B clearly offers more of both goods than bundle A, and therefore B must be strictly preferred to bundle A. So they cannot be indifferent at all. So again, with the three properties we have in place for the preference relationships, the indifference curves that represents any such preference relationship has to be downward sloping. Lastly, property 5, which says that the indifference curves cannot be thick. Imagine that we have a very thick indifference curve as we have here in figure C. Then what could happen is that you would have two different combinations of goods, A and B here, sitting on the same indifference curve, but because the indifference curve is thick, then it becomes possible that bundle B now sits towards the upper right corner of bundle A. Then again, non-satiation becomes a conflict against the definition of indifference curve. A and B cannot simultaneously be indifferent to each other by the definition of the indifference curve while satisfying non-satiation, where bundle B is strictly preferred to bundle A. Well, now with these 5 properties, what does that leave us? Well, what we would have is that we would have very, very nice looking indifference curves that are always nicely ordered as we have here in figure C, always downward sloping, always nicely layered, and will never cross with each other. And there we have a very nice looking preference map. And remember, regardless of how a consumer may prefer one good over the other, as long as the preference relationship satisfies completeness, transitivity, and non-satiation, it will be represented by preference relationships that will look as nice as this. Although the specific shapes of these curves will be different, they will all be nicely ordered and downward sloping and without any thickness.